see the link to that here in the box. Over the last year and a half, 2 years, I think we've accumulated quite an excellent review of the science in this area. And so an excellent place to go to for additional information, including the information you're going to be seeing here today. The most recent article that has appeared in that MASH blog is summarized in this particular graphic. And this was an effort to pull together the knowledge gained from 141 different studies looking at the substitution value of manure for fertilizer. And these were studies done from around the world, in the US, in Asia, and in Europe. And just 3 things I'll highlight real quickly and encourage you to go to the MASH blog and see more information on this. But in terms of some of the benefits that were reviewed by this study, what was the change in crop yields as the result of substituting manure? On average, a 5% increase. What was the change in nitrogen losses from this system? On the average, a greater than 25% reduction in losses of nitrogen to the air and to water. Some of the reasoning behind that reduced losses is illustrated here in terms of nitrogen's storage in the soil system being much more in that pool of microbial biomass nitrogen, or MBN, and some of the changes that occurred in that soil organic pool. So just a quick summary of what some of the findings were in that article, and I encourage you to take a look at least the summary that we put together on the blog, if not the entire research article, which is an excellent piece of literature to review. So you'll find those by going to that Soil Nexus website, and encourage you to take a look at that in greater detail. I think with that, I will end my discussion, and we will turn the presentation over to Charles Wortman and let him share some of his research and experience in this field. Charlie, welcome. Glad to have you here with us today. Okay, you're on mute right now, Charlie.
Right, unmuted.
There we go. Thank you.
Okay, I'm trying to get it into PowerPoint mode. There it is. All right, thank you, Rick. So I'm focused on manure use and soil physical properties this afternoon. We have a lot of soil property interaction. Soil itself
Charlie,
is, yes?
Before you get too far ahead, we're seeing the presenter mode. So if you want to go up to display settings.
Okay, thank you, Leslie.
Thank you.
So I want what, swap presenter mode in this way? Okay, like this?
Correct.
So soil is mostly inanimate, 99.5% on a dry weight basis. But it does provide habitat for much plant and microbial life, and also for a lot of chemistry. The science and managements of interactions of soil properties, such as physical, chemical, and biological, with crops and climate, is what we call agronomy. Now, I realize that all of you have had some sense of this, but maybe you haven't been accustomed to thinking of it this way. But it's the case, and for me, it's a very important consideration. There are some soil physical properties that are important to how much crop response and soil response we get from manure application. And that could include landscape position, soil texture, soil aggregation, susceptibility to erosion. And then there are physical properties that are affected by manure. Aggregation, for instance, soil aggregation, soil water infiltration, and some others. And then susceptibility to erosion is another physical property of much concern. We think about, if I go into a field that I'm not familiar with, the first thing I look at is, okay, where is this in relation to the landscape? And I think all of our states probably have publications similar to this in the upper right, Soils in Nebraska, where we have diagrams of soil associations, such as you see in the lower left, which tells us where to expect different soil types and different parent materials in the landscape. And you can get such diagrams in the county soil survey report, such as for Yankton County in the lower right. And the position in the landscape is implications for erosion and sedimentation, but also for response to manure application. Soil texture is a result of the sand, silt, and clay content of the soil. And we determine this texture classes using a texture triangle. And maybe we have a silt loam, maybe we have a clay soil or whatever. And soil texture is fundamental to other properties in their interactions. We might expect greater manure effect on soil physical properties for soils that are relatively high in sand content or high in clay content relative to many others. And with the diagram we have on the lower right, it's for, soil texture is something we can approximate in the field using different types of field tests. Soil particles can be very small, like clay particles. We cannot see them with a light microscope. We need an electron microscope to visualize them. And so if we did not have soil aggregation, our soil would essentially be a massive inert block. The size and strength of the soil aggregates are affected by other properties, including, especially soil organic matter and including soil organic matter. And this we've addressed recently in a new extension publication on soil management for increased organic matter, but also by management practice, including manure application. Often when I'm doing work in fields that I'm not familiar with, as in these two photos for Africa, I like to carry a number of things with me. And for the most part, they fit into a fisherman's vest, as you see on the ground here on the left and what I'm wearing in the upper right. But starting on the left here, I have some pH papers for testing pH, and next to it is a meter for electroconductivity. I don't use these anymore because instead I have a meter that does pH, electrical conductivity, and dissolved total solids. I carry a spoon for measuring, a GPS unit, a clinometer, and one that I most use is a tea strainer, and that I can use for a quick test of soil aggregation in the field. There are the various cups for various tests. A pocket knife is handy, a marker pen, a cylinder for measuring soil water infiltration, and then a probe that I can disassemble and pack in my luggage easily, for a probe for looking at deeper soil depths. And then finally, a simple thing on the right with a black handle made up of a bronzing rod. And this is flexible. I can fold it up to fit into my suitcase and unbend it when I'm in the field. But you can, easily and gradually, carefully work into the soil for the detection of any soil physical limitations to growth, whether it's a compaction layer or rock or something like this. So these are just some of the diagnostic tools that a person can be working with in the field. Susceptibility to erosion is, another property that's important to response to manure. Wind erosion and water erosion, with both we're most concerned about sheet erosion. That is the gradual movement of soil particles along the surface. With water erosion, it tends to be downslope. Some of this occurs to the raindrop splash effect, but then also the gradual movement of water downslope. Sheet erosion is our most erosive processes, but it's often not noticed. Much more visible to us are rill erosion, as we see in the photo in the upper right. Here we have a case of sedimentation in a terrace channel, showing that the terraces with the tile outlet riser, is very effective in preventing loss from the field. We have ephemeral gullies, which are very noticeable for us, and these would be typically closed with tillage every year. And then our permanent gullies. The aggregate size and aggregate stability, that's very important to soil susceptibility to erosion, as the small aggregates are easily carried and weak aggregates break down so that you have small or aggregates or dispersed soil particles. And that makes for easy transport, but also sealing of the soil for crusting and reduced water infiltration. So one study I'll speak of ran from 1999 to 2008. It was at our Eastern Nebraska Research and Development Center. The soil was a silt loam soil with a 5.5%. We had 21 plots, each of 0.01 acre. And then the runoff from these plots fed into 2 tanks where we could measure the amount of water and sediment and get our samples for analysis from each rainfall event or runoff event. There are 21 plots in total, 7 treatments with 3 replications. And I won't go into detail on the treatments, but with many, there was composted feedlot manure applied for 3 years in sequence, 99, 80, and 81. It was applied at heavy rates with the intention of meeting the nitrogen need of irrigated corn. So it's an unusual practice, but the study was set up this way. In the next few slides, we're looking at the effect of compost on runoff, erosion, and phosphorus loss. So in this figure, we have 2 pairs of bars. The blue is for where compost was applied, the purple with no compost application. The first pair is for runoff loss during the 3 years with the annual application. And the second pair is for the 4 years following application. So we see that during application, the years of application, our runoff was reduced by about 60% and a 40% reduction due to the residual effect. Here the bars are colored differently, but again, we have compost compared to no compost, both during the years of application and during the 4 years following application. And it's for sediment loss. And we see that during the years of application, the sediment loss was reduced by about 40%. And during the residual years, 60%. Using these results and results from other studies, we estimate that there's approximately a 2% reduction in runoff and erosion per ton per acre per year of dry weight of manure application. For the effects on phosphorus, well, first of all, let's look at the effect on soil phosphorus in the top 1 inch. And we used the top 1 inch here because that's what's susceptible to runoff and erosion. Where we had put on the compost, it had brought the soil test P by Bray 1 up to 500 parts per million compared to 20 parts per million with no compost applied. So a 25-fold difference. If we look at the loss of bioavailable phosphorus, however, we see that it is higher with compost applied, both during the years of application and during the 4 years following application. But it's not near so great of a difference as we would expect from the soil test values. In years 5 and 6 after the last application, there was still reduction in sediment loss, 2.8 times as much sediment loss with no compost applied compared to where compost had previously been applied. Other treatments allowed us to look at the time of application and incorporation. And we did not find any effects on runoff or losses of sediment or phosphorus for winter versus spring application without any incorporation, just applying it to the surface. And then with spring application with and without incorporation. And this is, the spring results are well supported by results from ISU, Iowa State University, where if you have 1 or 2 moderate sized rainfall events that do not cause runoff, before you have a runoff event, you get enough reaction of the soil with the manure that you do not have an increase in phosphorus loss with surface application as compared to where the manure was applied. So in summary here, we can say that manure application tends to reduce sediment and runoff, but to increase the runoff phosphorus concentration. The actual P loss, the quantity loss, may be increased or decreased, and it depends upon, does the reduction in runoff and sediment loss fully compensate for increased runoff P concentration? In this study, the greatly decreased erosion and runoff did not compensate for increased P concentration and runoff, and the P loss was somewhat greater where the compost was applied. So some of this information, specifically on erosion, the effect of manure application on erosion, is integrated in some decision tools, such as the NRCS Russell 2 for erosion estimation, and the Nebraska Phosphorus Index, which also has a calculator for erosion loss. So we saw that manure application reduced runoff and erosion. What about its effect on soil aggregation? Well, to look at water stable aggregation, we use a set of 4 or more sieves, which are stacked, and the soil is put on the top one, and then it's the set of sieves is rotated through water, up and down in water 50 times. And our sampling is from the 1-inch depth. For dry aggregates, we measure these to look at determine the wind erodible fraction, or the WEF. We consider anything that is not in aggregates greater than 8.4 or millimeters, or greater than 0.33. Let me repeat that. If it's less than 0.84 millimeters and less than 0.00033 inch diameter, we consider it to be WEF, wind erodible. And we determine this by sieving dry soil through a stack of sieves and doing the calculation to get the amount of soil in WEF. So one study on aggregation that we'll look at is where we had treatments with composted feedlot manure, stockpiled feedlot manure, and no manure applied. And these on the x-axis of the figures are designated as C for compost, N for none, and M for stockpiled manure. We had this with tillage and no tillage, tillage for incorporation and no till. And we did it with Crete upland soil, which is silty clay loam, and Nottoway bottomland soil, alluvial silt loam, but both prime agricultural land. We collected samples periodically starting 2 weeks after application and continuing for 150 days. One of the results was that there was increased water stable aggregates, large aggregates, already 2 weeks after application. If we go back to the figure and look at the y-axis, we see we have percent of soil in soil aggregates. Our soil aggregate size is based on those sieves that we used. For the black color, it's greater than 2 millimeter diameter. The gray color is 0.25 to 2 millimeter. The white is 0.053 to 0.25 millimeter. Now 0.53 millimeter, that's about the size of a human hair. So we're talking, quite small. If we look at the results and compare the none with the compost and the manure, raw manure, the stockpile manure, we see that the black is somewhat affected. Not a large fraction of the soil is there, but that's one that's most affected. And we see that the total in what we call macro aggregates, that is greater than 2 millimeter, we consider to be large macro aggregates, 0.25 to 2 is small macro aggregates, and the white represents micro aggregates. The result is that 39% of the soil was in macro water stable aggregates with either compost or stockpiled manure applied, compared to 33% with no manure applied. We did not find any difference between compost and the stockpiled manure treatments. They appeared to have similar effects. A second study was conducted in Northeast Nebraska. Again, we sampled to 0 to 1 inch depth, and it was a silty clay loam soil. And their manure had been applied for 4 years continuously. With feedlot manure, it was 20 tons per acre per year. And with swine manure, swine slurry on a dry weight basis is 2.7 tons per acre per year. We found there that soil in the macro aggregates, and again, larger than 0.25 millimeter, was 42% with manure application versus 35% with no manure applied. We did not find a difference in manure type, and there was no difference in soil of less than 0.053. That is, there was some effect on micro aggregates. So in summary, manure effects on soil physical properties depend on the initial soil properties. Manure application tends to reduce erosion and improve water infiltration, but increase runoff phosphorus concentration. This may result in a decrease or an increase in runoff P loss. The manure effect is primarily to increase the macro aggregates, water stable aggregates. And that effect can occur very quickly if there is a rainfall event, in one case, 2 weeks. Thank you. And with this, I'll turn it over to Linda Schote. So what do I do here? Stop share.
There you go. And Linda, glad to have you up next here. If you want to pull up your PowerPoint, we welcome you to share your information. I might just mention that Linda's information, if you'd like to go through it more, or even summaries of Charlie's information, are both presented on the Soil Nexus website as part of the MASH blog on that site. Linda, the floor is yours.
All right, thank you. So I am, as Rick said, an extension graduate research assistant at the University of Nebraska-Lincoln. I'm a PhD candidate, and this was part of my dissertation work. So I'm just going to summarize the literature review that I did on the effects of manure and biosolids on soil quality. Okay, so first I just wanted to give a little bit of background information about why soil quality or soil health is important. So the FAO defines soil health as the capacity of the soil to function as a vital living ecosystem that sustains plants, animals, and humans. And it's really the intersection and consideration of soil physical, chemical, and biological properties. It's the biological properties that make soil a living system in addition to the plants that live there. And soil really has to have good quality in order to provide nutrient cycling, proper water, and physical support and habitat for biodiversity to really support plants, animals, and humans. And there's been a lot of focus on how practices like cover cropping and crop rotations affect soil quality, but not much has really focused on the effect of manure on soil health properties. And in general, practices that increase soil organic matter increase soil quality. And as a small spoiler alert, manure increases soil organic carbon. And so it is in soil organic matter. And so it is a practice that has the potential and does improve soil quality. So the objectives of this literature review were to summarize the results of short and long-term studies reporting the effects of livestock manure and municipal biosolids on chemical, physical, and biological properties of the soil, and to also look at other indicators of soil quality like climate resistance, the resistance to drought and heavy rainfall events, crop yield and quality, and things like that that are also indicators of good soil quality. And I also wanted to, so that the first objective is really to assess the current state of the science. And the second objective is to really, where does the science need to go now to move forward? So the second objective was to describe future research needs related to manure and soil quality. So just very briefly, we looked at a lot of different soil physical, chemical, and biological properties, and they're all listed here. And basically any manure study that looked at one or more of the effect of manure on one or more of these properties was included in this paper. And I have listed 219, but I'm working on improving this literature review more. And so it's a little bit more than that. And there's also more, there's 175 that are relevant, where the only thing that was changed between treatments was manure application. And then there were 15 review articles that were also included, but those review articles didn't really investigate the effects of manure on biological properties. And a lot of those review articles are several decades old. So just kind of focus more on biological properties and also what is the newest research out there. So here's just a table of the number of studies for all of these properties. And so most of the previous research has really focused on the effect of manure on chemical and physical properties like soil carbon and organic matter, bulk density, aggregation, water holding capacity, and then NPK are also had quite a few studies as well. And there were 66 that looked at biological properties, but within those 66, there were a number of metrics, and some of them might have only had one. So the majority of those biological studies only looked at microbial biomass carbon and not that many others. And so the other indicators that we looked at were microbial biomass nitrogen, respiration, nitrogen mineralization, PLFA, which is for diversity, and microarthropods, nematodes, and earthworms. And these studies were worldwide and used a lot of different manure sources and on many soil types and had a lot of different climates. And so to summarize, in general, manure increases soil organic carbon. It increases nitrogen, phosphorus, and potassium, and also contains a lot of soil micronutrients. The effect of CEC and pH varied because the effect of the manure and biosolids is highly influenced by the chemical properties of the amendment and the initial chemical properties of the soil. And so for CEC and pH, it really depended on what the soil type was and what kind of climate it was, and then also a little bit of what type of amendment was being used, and the amount of amendment that was applied. But I did want to talk a little bit more about soil organic matter, because that's really what drives one of the main factors of improving soil quality. And this is just a table or a diagram that I pulled from one of the articles. And it just shows that when you increase soil organic carbon through organic amendments like manure, there's a lot of really neat things that happen. You enhance the water holding capacity of the soil, increase nutrient retention, and improve the structure and biological quality. And all of those will eventually lead to an increase of soil organic matter, because as biology breaks down and consumes that carbon, it stabilizes and will eventually become organic matter. And manure increases soil organic carbon 10 to 100+%. It's really variable because it depends on a lot of factors like climate and soil type. But manure does increase organic carbon because there's a lot of carbon in manure. And this is compared to inorganic fertilizer. And another interesting thing that I uncovered is that about 20% of the carbon that you apply with manure will persist after the first year. And so not all of the carbon will remain in the soil system. It's consumed, it's lost, it's respired, but 20% will remain. And that's eventually what builds up and allows soil organic matter to be created. So for soil physical properties, aggregate stability and infiltration increase, and bulk density decreases. And again, water holding capacity was kind of, in some cases it increased, in some cases it didn't. And it was very split, and it was very dependent on the soil type. Likely going back to what Charles said about about having more effect on the clays and the heavy sands. For biological properties, there's really three ways to assess biology in the soil. There's abundance, so how many bacteria or microbes are there, and included in abundance was bacteria and fungi, earthworms, and nematodes and microarthropods. You can also assess it with diversity, which was done through PLFA in many of these studies, or activity, which was done with respiration. So how many are there, who's all there, the types of community, and then also what are they doing? And in general, manure significantly increased bacteria and fungi abundance in soil compared to inorganic fertilizer. It increased respiration, it increased earthworm and nematode populations, but didn't seem to have an effect on microbial diversity or upper order microarthropods. But there weren't that many studies that looked at those. And so, so why is all of this important? As Charles said, the soil is 95 to 99% mineral particles, and depending on where you live, 1 to 6% is soil organic matter. And in that soil organic matter, there's stable humus, ready and decomposable plant matter and things to break down. But there's also 3 to 9% is bacteria, fungi, fauna, and other soil biology. And so it's a part of the soil organic matter. And they're really important for nutrient cycling and just in plant health and growth. And so just to go a little, I really like this diagram of the soil food web and how it all impacts each other. And I think this is a great way to show these biology results. So manure significantly increases soil organic matter, which then allows that bacterial and fungal populations to increase. And these were measured with soil or microbial biomass carbon and nitrogen. And in comparison to inorganic fertilizers, manure increases this population 10 to over 100%, just like the organic matter increases. And then because those populations are increased, does not necessarily mean that the arthropod populations are increased up here, just a little bit out of order, but the nematodes that feed on fungal and bacteria are increased, and the root feeder nematodes were mixed. There was only a couple of studies, and they were pretty, one showed an increase of those types of nematodes and others showed decreases. And then earthworm populations also significantly increased. And this is for long-term and short-term results across many soil types and manure sources. The fungal and bacterial populations increased within a year of manure application. And so just some future recommendations for this type of research is that the quantification of biological metrics should be included because the biology is really important in nutrient cycling, and not that many studies looked at that. And I also think a lot of the studies that I looked at applied pretty high rates of manure on an annual basis, where in many cases phosphorus, there's a lot of excess phosphorus, and likely a producer would not apply that much manure that often. And so I think we need to look at what are the effects of a single application of manure, or is there an optimum frequency for application to improve certain soil properties? Can we leverage manure to improve certain properties to address issues in a field? And then also to provide discussion that really relates this research to management decisions that are relevant to crop producers to really increase the utilization of this value product. And so I just wanted to quickly thank the funding sources for this project, the Soil Health Institute and the North Central Region Water Network, and also the two undergrads that really helped organize and identify these articles. Thank you.
All right.
I will turn it back over to Rick.
Okay, thank you, Linda. And Linda and Charlie, thanks for the excellent information that you've shared. I do want to remind everybody that's in attendance today, if you've got questions you'd like to address to the speakers, post those in the Q&A box. If you want to access that, just take your cursor down to the bottom of your Zoom screen. It should expose some icons, and one of those should be the chat or the Q&A window, and I'll be monitoring that more closely for questions that we'll try to get answered. Also, there's going to be a set of polls that appear on the screen, and really appreciate if you would take just a minute or two to share some feedback on today's discussion. So thank you for that. I do have a couple of questions, one that came in before the meeting actually, and one that came in during our discussion today. So I'm going to start with those. Charlie, I believe it was Michael that asked about the increase in P loss in your studies of erosion and runoff and P loss from those 21 sites. If the soil erosion and the runoff reduced, why did we see an increase in P loss?
All right, can you hear me or do I have to do something?
You're in good shape.
Okay,
thank you.
Thank you. Well, with that compost application, of course, there was a lot of phosphorus applied. And as I pointed out, that increased the soil test phosphorus in the top 1 inch from 25 parts per million to 500 parts per million. And so that phosphorus was very available to runoff and erosion loss. So I think that answers the question, doesn't it?
Yeah, I think so. And it was a combination that increased source at the surface caused the increase. The reduced erosion and runoff caused that, tended to offset a big chunk of that increase.
Right, that's right, Rick.
Okay. Very good. So thank you, Michael. I hope that answers your question. Please post your questions in the Q&A box. This question came in before the actual webinar. I thought we would want to get to. In order to change the organic matter in our soils using manure, it often is a matter of years, maybe even decades, for us to see something like a 1% increase in soil organic matter. But yet, Charlie, you saw some changes that were occurring in the first couple of weeks of your experiment. So are these differences in the properties that we're seeing a result of just strictly organic matter change, or is there something else going on here?
The soil organic matter change would not be very great. The quantity of manure, I forget what the rates were, but it would be very small compared to what the organic matter was out there already, which was around 3%. If you do the calculation, it means, you know, well over 500 tons of organic matter. But it was that fresh organic material and its reaction with the soil particles for the improved aggregation is what we saw. So not so much a change in organic matter, but the reaction of that new material with the existing soil.
Great, thank you. Linda, anything else you'd like to add to that discussion?
Just that the biology is also probably playing a role, increased fungal and bacterial populations with that new material. It's just the reaction with that new material. A lot going on.
Okay, yeah. There is an excellent article that was written by a couple of soil scientists from the Michigan State University, wrote an extension publication on this topic. I don't know if I can find that to put it out for you, but you'll do a search, you might find it. One of the things that those authors suggested is that manure provides an energy source for a real explosion in the microbial community in the soils shortly after manure application. So it's that explosion in the microbial community because they have the energy to multiply, reproduce, become more active. And that was their thoughts on why, explaining the quick changes in soil properties that occur that would have occurred long before we really increased the soil organic matter substantially. That seemed to follow with some of your understandings, Charlie or Linda?
Well, yeah, some increase in soil microbial activity. And as Linda said, especially with fungi, they would contribute to the improved soil aggregation quite quickly. But microbes, they need adequate water, adequate temperature, adequate air, adequate energy source, which is generally an organic material, adequate nitrogen. Those are the 5 main things. And if one of those is limiting and you cause a shift, you can get a very big burst in microbial activity.
Okay, great. All right, Jennifer has a question. Charlie, you talked about changes in soil erosion. She didn't quite understand what was the science behind that change in that reduced erosion loss.
Well, we think it's primarily because of soil aggregation, and which means improved water infiltration rate. We saw that with the less runoff, greatly reduced runoff, but then also the better aggregation, less resistance to movement by water. That is more stable aggregates, larger aggregates, easier, more difficult for water to carry the sediment down slope. We did one study I did not mention due to shortage of time was where at that same site, we did look at soil aggregation. And this was 4 years after the compost application, the last compost application. So we're looking at a residual effect. And there was a difference in the what we call the macro aggregates, the water stable macro aggregates. So this improved aggregation was continuing to give us improved runoff or improved water infiltration and less erosion.
Excellent. Linda, anything you want to add to that?
No. Yeah, I think that was good.
Okay, good deal. Please add questions that you'd like to get answered to the Q&A box. Got one more here, Charlie. Or Linda, I'd like to run by you. I guess I'd like both of you. We've always thought in terms of applying manure on fields where there's a nutrient benefit to be gained, whether that's nitrogen or phosphorus. If we're beginning to think in terms of prioritizing fields based upon the carbon that's in the manure and the carbon benefits, what would be the priorities you might set for those fields to receive manure first?
Well, Linda, I can take a shot at it. My father and the neighbors and the people in the neighborhood, they recognized that there were certain soils where they could get a better response. So my father had a farm with very diverse soil types, including some sloping land that had once been, badly eroded and was calcareous soil. He knew that he could get his best response to manure there. And that's still true now. Sometimes it might be a heavier clay soil. You want to improve the aggregation. Sometimes it might be a relatively high sand soil where you want to improve it. So it varies farm to farm, but definitely, you can expect differences in yield or differences in both soil and crop response to the manure based on soil type. With the erosion study I mentioned, for instance, we did not have an effective manure on crop yield. It was already prime land, generally adequate nutrient availability, and even though the water infiltration was improved with the compost application, it seemed that water was not a factor. And anyway, it was an irrigated site. So that was a case we did not see any benefit to the crop, but there was a benefit to the soil in terms of reduced susceptibility to erosion.
Great. Linda, do you want to add any thoughts to that?
I would also echo using it on eroded. Well, I would say to utilize manure on eroded land as a way to increase the soil carbon and improve the soil biology, which will then positively impact, it'll increase your aggregation and decrease future erosion potential with that. And I think it's a good treatment for those kinds of soils. I mean, manure has a lot of benefits, and I think it could be used in a lot of to solve a lot of problems in fields in general.
Great. I'll share one observation. It was with a crop farmer here earlier in April that had an arrangement with a local dairy farm. That he was providing silage to the dairy farm, and the dairy was providing manure to him. This individual identified one of the first changes he saw in his fields was fields that he had a history of areas in the field that would drown out. Water would pond in the field. You'd have drown out spots in that area. And very quickly after using manure on those fields, those drown out spots would become smaller and smaller and disappear with time. And so one of the places he was looking for those fields that tend to have those low spots that drowned out frequently and targeting those fields. Any reactions to that observation by that crop farmer?
That does sound feasible. I wouldn't say that would be the case for all situations where you have occasionally drowned out, but certainly in some cases, yes, that you would get that somewhat improved aggregation and better soil aeration, maybe better water movement through the soil.
Okay, all right. Any other questions from our group today? I've been watching the chat Q&A box, and I think we've got all those questions answered. Leslie, am I missing anything here that we want to run by? Okay, I do see one question here. Can the speakers clarify what sources of manure are typically used in these studies? And maybe relevant to that, does it make much difference in terms of the source of the manure and the benefits that you've seen?
So I can, in the literature review that I did, there was a lot of manure sources. Primarily I would say the majority was cattle manure, beef manure, but there was also a lot of poultry, swine, and then there was manure, like beef manure mixed with straw, which is used a lot in Asia, and also composted. And my review also included municipal biosolids, so human waste. And there really wasn't a difference in, broadly speaking, in the different types of manure in terms of a lot of the properties. Because it's so dependent on other factors like the initial soil conditions and the climate. I did not see many differences between composted and non-composted manure in terms of the other properties. I'm sure that Charlie can speak more to the differences between those two for the work that he's done, though.
So I spoke about compost compared with uncomposted feedlot manure and swine manure compared with feedlot manure, and we did not see differences in effects there. Another study that I did not get to, we compared 6 different organic materials, including composted dairy manure, 2 types of feedlot manure, poultry manure, actually it was 7, I guess, and then 3 municipal biosolids, all processed in different ways. One thing that was different about the biosolids compared with the manures is that the biosolids had higher cellulose, lignin, and hemicellulose content compared to the animal manures. And I was a bit surprised by that, but then if you think about it, we flush a lot of paper down, and maybe there's some hair there, etc. You can speculate on what causes the high lignin and cellulose content. But and we did find that very much affected the rate of nitrogen release from the organic nitrogen that was applied, where with the animal manures, we had almost twice as much of the organic nitrogen available to the crop in the first year as compared to the biosolids. With the soil aggregation, we did not see much effect, but then we found that already the soil was very highly aggregated and there just wasn't much room for improvement anymore. And I think that's the case for a lot of our agricultural land. If it's producing 240 bushel corn really fairly consistently, it's, you know, you can expect it's pretty well optimized. Thank you.
I think we have one last question I'm going to try to get to, and then we're going to call her the end for the day and thank the speakers for the knowledge that they shared. It was shared, one last question was that we've heard a lot about the positives of animal manures and their benefits to soil. What about some of the negative interactions between excess nutrients and others? So this is not a black and white issue. Anybody want to share kind of on the negative side what we have to be concerned about and where we need to how we avoid those becoming too big of an issue.
Well, there is the concern with excess nutrient application, of course. I've observed some fields near feeding operations where the groundwater had very high nitrate levels, for instance. And of course, there's the phosphorus issue. Hormones and antibiotics may be of concern. Although with antibiotics, we need to keep in mind that even pristine prairie soils have antibiotic resistance there, because that's where we got our antibodies, was from soil microorganisms, the early antibiotics. But those are still something we need to keep an eye on. So yeah, excessive nutrient application, the implications of the hormones, and more importantly, antibiotic application and the potential for enhancing resistance.
So nothing is ever perfect, always a mix of gray, any of these issues. But anyway, today I hope we highlighted some of the real positives of animal manure from a soil health perspective. I really appreciate the expertise that Linda and Charlie have shared with us today. And hope that you'll be joining us on that third Friday again in June for our discussion of irrigation of animal manures and the impact on and pathogen transmission through irrigation systems and the research that's being done at the University of Wisconsin. So thank you all for joining us, and hope to join forces with you again here in another month. Have a good day.
Thank you.